hate doing this. It's good. It's on private mode though, so only you guys can see the link for it. It's not public. That's a good thing. Okay.
Put it on the web.
I celebrated those guys.
Yes.
Did you?
My brother
So you get them
Exactly, I hate that. And then like the night after the test, yeah.
It's a new one.
keeps flipping around all over the world. It will slow down.
I'm not a part of it.
On that,
I don't know.
you won't play.
My question is that
as long as you download it.
in general, I don't
Versus
know.
downloading the patterns and
I will look, and I'm looking. Give me one second. But I
The bad thing is now they know it's before they just this is the accurate stuff.
Better yet.
unfortunately, I think as far as assignment, you can't change it.
I can't.
I do that. But I don't. Sorry.
Sorry for this volunteer crap. Can we discuss it in my office on Monday or Friday?
I think it has to do with
So just go next Monday.
radiation that's emitted from the job.
Don't worry about it.
Radiation. Because that's the effect of spinning. It's emitting. It should be. I don't know why. Let me look it up. I'm curious. I'll look it up. I'll tell you. I'll look it up. Momentum. Yeah.
Oh wait, what's that? You don't want to.
The thing is, which one's the second variation?
Yeah.
Obviously, I was going through the examples of the book. The same examples, they have the that section.
Well, yeah, but he may say to you, use. He may give you the same question, and say use variation. Grounders method.
You can use the first one.
Yeah, but there's some you can't.
Yeah, it's 10 some, but most of them you can use.
But I think you might as well just keep the simple ones.
Okay.
I was thinking
2:31.
you said that you had the nature
All right.
question.
So any
But I've
questions
never seen
from
it in any couples.
last time? So I realized. See, exams on Friday. It's photocopied. It's very nice. It should be straightforward. Like I said, these exams either you'll be able to do in 11 minutes or 11 hours, depending on. I mean, for the first exam, how long really did it take anybody? If you study, you do well. If you don't study, you won't. But that's true with. So let me actually. A lot of interesting emails I got about my lecture on
The
Friday,
board
which is a
doesn't
good
cover
thing.
in this. So if you can.
And I realized that I started to introduce manifolds without actually giving you a motivation like why I'm doing this. Singh came to my office today and asked me, so thank you for that. Our basic dynamical system is always written in. So x prime vector, that's what we have been doing, that's what we will be doing, and that's the vast majority of dynamical systems you see are always written in this form. But as I have been saying, even in the linear case, these are vector fields. So x is a vector, f is a vector field. So what I mean is a function of a vector. So if your phase space, the phase portraits we've been drawing in the xy plane, are just linear vector space. So what I've been doing so far in the linear case is just drawing a bunch of solutions in the xy plane. It's fine. If you know, if I give you some vector here, call that v, you know how to write this vector in this plane in terms of the components of x and y, right? It's just going to be, so if this is, let's say AB has its components, you know that B then is AX hat plus BY from your linear algebra. So in linear systems, it's great, it's fun. In nonlinear systems, which is the general case, your phase space could be like this, a circle, or I don't know how to draw a sphere, so imagine this could be a sphere. I don't know, how would you draw a sphere like that? Or a cylinder. Or some weird geometric shape that's not linear. But the fundamental equations are still vector equations. So now I must ask the question, how in the world do you define a vector on a curved surface? That's the reason why I have to introduce this machinery called manifolds, which is a part of a broader subject of what we call differential topology. It's because I want to really answer this question. What does it mean to define a vector on the surface of a sphere? So on the surface of the Earth, for example, how do you define a vector? Where are its basis vectors? On the surface of a cylinder, how do you do it? And then you have the other problem, which we won't get to in this class, which is more suitable for a differential geometry class. You see, in the planar case, in the flat plane case, I can take my vector, if I move it, it's still the same vector. As long as I don't change the orientation or the magnitude of the vector, it's still the same vector. I can move this vector here. It's still parallelly displaced. But now, let's say I have a circle. The challenge is, I would still like to do this. How would I move this vector along the surface of this circle, or around the circle, without changing its orientation or magnitude? So this is a very big problem in differential geometry. It's a very nice answer, but to answer this specific question, you need to know the material of this course. So you won't be able to answer till next week. But that's why. So your phase space in general is more generic than just some planar system. You could have a sphere or a cylinder or some, even something like a torus or something like this. How do you define vectors on these things? So what does it mean to have that fundamental equation in more complicated geometry? So that's why I need to introduce this new topic of manifolds to make this idea more concrete. But this idea, if you want to read about it, it's called the problem of parallel transport. It's a well-known solution, but you need the materials of this course to answer it. And it is possible to do this operation, to move this vector around the circle in a parallel way, but it requires some more things that we actually don't need to know for this course. So for this course, all you need to know is, be puzzled with, is how do you define vector fields on more general systems. So we'll get to that in a class or so. That's why I'm doing this, not to make your life difficult. Anyway, so let me continue. Does anybody have any questions? So think about that. How in the world, if you have some general, curved surface like this, how do you define a vector on the curve? So think about me continue on with the some of the definitions I was doing last time. So I believe I ended last class talking about the house dog. Should I correct you? So I will continue from there. Okay. So remember, I will just write it again. I will do a better job of erasing. Okay, so house dog, just to recall it from last time. So we said that any two distinct points of M can be separated by neighbors. That was what I concluded with. Okay, so continuing from there, I will call a family U alpha, so that's my family of open sets. U means open set from last time, if you remember. And alpha is just an index on the set. A family of open sets. So remember, we have our manifold, we have a bunch of points in this manifold, and it's also, so each point or distinct points can be separated by open sets. Okay? So you'll have a bunch of open sets in M. And this family of open sets, we say forms what we call a covering. Of M, if M can be written as the union as follows. So if I can write M as the union of my family of open sets, then we say that this family forms a covering of them. So all the possible open sets, it covers the manifold. And further, we say that a covering, call it R, is finite if U alpha contains, as you can imagine, a finite number of elements. And further, this is just this point now that I'm about to make is not really, we don't really need it, but I will just for completeness sake. So further, we say that a topological space which I've been denoting as M so far, is compact. Is compact if it is possible and any open covering contains a finite number of finite covering, not a finite number of elements. We say that covering contains a finite covering. That's what I want. So that covers, yes.
So in the family of U alpha, so that every element which is open set is in the space M.
Yes. Very good. So what I can do, instead of talking about my space M in terms of the points, I can describe it completely by the open sets. That's what this says. So So you can decompose M in terms of covering all possible. So this covers my definition of topological space. So let me extend this now a little bit, okay? So let me talk about maps of sets. So maybe you saw some of this in calculus, maybe not, but anyways, let's do it. So let U and U prime be two sets. And suppose, I'm doing a lot of writing today, I just realized. And suppose that there is a map from U to U prime. So two sets, there's a mapping that goes from U to U prime. Okay? Which, and what does this mapping do? It assigns to each point, for lack of a better terminology, I will call this point P. To each point P in U, a unique point, P prime in U prime. So just the function. It uniquely maps one point in U to uniquely one point in U prime. So P to P prime. Okay, and we call this map, as you may guess, F. That's what you typically see. So our notation would be something like F goes from U to, and you've seen this a gazillion times. Hopefully. So then, based on this definition, we can say some things about that. Everybody right now is wondering what happened to the differential equation. But they're all there, I promise. Okay. The nature of F can be classified as follows. Number one, so there's just three characters. So if F is such that for every P prime in F of U, there is exactly one P in U that maps to P prime, we say that F is what? Does anybody remember? If my function, not the onto the other one to one, right? Or something more advanced textbooks call it what?
Inject.
There's one more. Which one is it?
Subject. Subjective.
If it's just one to one. Who said it? Injective. Yes, very good. I can never remember, I always have to look it up. But one to one injective means the same. And further, so that's one problem. It's all the French people's fault that these terms were introduced. It's actually Bourbaki in the 1920s. He was not satisfied with one-to-one and on-two. He started terms like injective, surjective, bijective. Yeah, they really messed up math for a lot of people. Everybody was fine with limits as x goes to a, and then he decided, no, epsilon delta, that's the right way. So, yeah, the French school and the Russian school of mathematics, from that point, they had a big divergence. Yeah. There's a joke, if you go to a Russian school, ask any high school student, what is 5 plus 3? They'll say 8. But if you ask a French elementary school student, they say 5 plus 3 is equal to 3 plus 5 by the associated property condition. Yeah. I don't know, it's because they do this types of things. But it's useful. I mean, you can understand these things without it. So. Okay, another possibility is that if f of u is equal to u prime, we say the map is now surjective, the other way, onto. Or onto. And the reason is that it simply maps u to u prime. And then finally, you can imagine, and you know this, if 1 and 2 are both true, it's 1 to 1 and on 2, then we have a bijection. Okay. So if f is both injective and surjective, we know it's bijection. So 1 to 1 and on 2. So mappings of sets in this even general context works exactly the same way as for functions, as you know. Okay, so that I just want to introduce some of this terminology because it will come up. So let me now move on. And any questions? So this should just be a review essentially. So our background is a bit different, but the basic ideas are. We're almost there where we need to be. I have to do a few more things. Okay, so now a separate, I guess, heading, but I don't know what to call it. So just put a line there. So let Rn, your famous, well-known Rn, be the set of all. If I use the word n to go, does everybody know what I mean? Yeah. From your multivariable calculus class? I just mean some vector that has n elements. Python programmers would know n tuples. So set of L n tuples are of real numbers. That's what you really mean by Rn. That is the set of all. So I will denote it like this, okay? x1 all the way to xn. I'm putting my label on the upper index instead of the lower one because I want to save it for later. So this is not x to the power 1, it means x1. It's easier, you'll see later on. If you don't like it, you can switch it, but I'm used to doing it. So this is just my label, x1. You write it like this, but for reasons you will see, I write it on the upper. So it's just a label. So it's just coordinates, right? And tuples are just your coordinate vector. Okay. Where each xi is just an element of R1, so it's just a number. For I equals 1 to n. Okay. Now, I will extend what I've already introduced in combination with this. So now, let M be a set of points, as I drew for you last time. But now I'm writing it down. So given this, let M be a set of points. So just some set with some points in it. We say that M is a manifold if, I will write on this. If for every point of M, what can we say? If for every point of M there is in open neighborhood of that point for which there is a continuous one-to-one and onto map. Call it F to some open neighborhood of Rn. I'll draw this for you in a second, but intuitively try to understand. You have M, which is a bunch of points. It's a set of points. My claim is that M, or by definition, M is a manifold if around each point there's an open neighborhood that maps to an open neighborhood of Rn. Okay? Think of it like this. So I'll draw this for you in a second. But try to visualize what this is. And come back. Okay. And further, if this map, I'm saying it's continuous one-to-one and on-to, so it's a bijection. And further, we assume that F inverse is continuous as well. So from 2 classes ago, when we talked about transformations of coordinates, what was the name of a function that is both bijective and has an inverse continuous inverse?
That's not.
No, very good. Okay, good. You're paying attention. That's the good. So indeed, we say that if we also are assuming the inverse is continuous as well, so therefore F is a homogeneous. So most of this you've not seen before, so I'm just introducing terminology. It won't show up on your exam. Don't worry. It could, maybe. No, it won't. It's amazing to me how many people have written textbooks on differential equations, but most of them just say the same thing in different forms. But at least this gives you some idea of what is really going on in ordinary differential equations, and how much great structure there is actually behind it. But right now you still won't see it, but you're starting to get an idea of it. Okay, so the point is the following. With all of these conditions satisfied, this is the most important one. So if every single one of these things I've written down is true, then what? Then a local region of M can be made to look like Rn locally. That's the point. So you can start to see where I'm going with this. I can take any manifold, and within some open region, I can make it look very much like Rn. And that's my vector space. So I'm starting to get where I want to go. All right. So let me build on this idea. Maybe you start to form the picture in your head a little bit. So let me make it more clear. Okay. So now consider 2 regions. You can consider more, but I will just consider 2 for now. And call these regions, for lack of better terminology, U and V. Capital U, capital V. And consider the following mapping. So one mapping I will call F. It goes from U to Rn, motivated by these definitions. And I will consider another mapping called G that goes from B. So 2 mappings. U and V are regions of M, and they map from that region to some open region of R, based on these definitions. Fine. Now what? I will also, just to be safe, I will assume that U and V have a non-empty intersection. We talked about this last time, but I will just make it more explicit. All right. So what can I do? Maybe I should write it out first and then draw a picture later. So I'll do that. That's a better approach. Now, I will ask you to choose some point. Call it A. In my function that takes as its argument U intersect V. So some point in this function, which is a subset of R. And take the coordinates in that Rn to be, I will just denote this as x1 all the way to x. All right. Now, oh, so much writing. It's okay. It's just for maybe one inverse. Now use the inverse mapping, F inverse, to map this point A back to U in F. And in fact, back to, let's say, point B in U intersection. So I'll draw this up here. You'll see it. It's more clear. But I have to explain it first in words, so you will understand the drawing. Because also the chances are I may draw it and then nobody will understand my drawings, which happens a lot. Okay. And further, since B lies in this intersection, we can now use our other mapping, G. We can now use G to map B, but now to some other point, call it C. In the region G, U intersect, where the coordinates of this region, I won't denote by x1 to xn, I'll call it y1 to y. Where these coordinates, I will denote as y1 all the way to y. So what have I done in doing all this complication? What I've done is the following. Well, I don't need to write it again because I've written that already. So by the properties of F and G, we have a one-to-one mapping which is actually G composed of F inverse. If you actually look at what I've done, based on this information here. We're using F inverse to go back. So what I've done is construct a mapping, G composed of F inverse, and that has this form. But I promise it will be clear in a second. Maybe it's clear? From the region, F, U intersect V of in Rn to another region G, U intersect V of R. I'll give you a hint. I've done something. Originally I have coordinates x1 to xn, and now I have new coordinates y1 to yn. What have I basically set up here? Yes, but which coordinates of which Rn to which coordinates of which Rn? Anybody see it? Volunteers? I've done something here where I start off with coordinates x1 to xn, and then I get a relation that tells me how to get some new coordinates y1 to yn. I've defined a coordinate transformation. This is what you mean by change of coordinates. So what we've done actually, in this process, and I'll draw this for you. In this process, we have actually defined a coordinate transformation. So, in your second year calculus course or first year calculus course, when they asked you, you have x and y, and you want to switch to polar coordinates, this is actually what you were doing. By defining x as r cos theta and y as r sin theta, switching from xy to r theta, this is actually what you do. But this is the general reason why this works. So you can imagine it. So something like, so y1 is actually y1 of x1 to x. So we know how to get our new coordinates in terms of the old one. So therefore it's a coordinate transformation. Okay, so let me draw what I've written here in pictorial format, and hopefully it will be. Okay, so as I said, M is just that. It doesn't have to be a circle, it can be anything, but I will draw it. This is M, and it's a collection of points. Consider some set U. So I'm just drawing now a picture of what I wrote in words, so hopefully it'll be good. And some other set, call it B, and the intersection between the two is not. Okay. And as I said, call this intersection B, which is just U intersecting. Fine. I said there's a mapping that goes from U to some local copy of Rn. So call this Rn. And here is applicated. So maybe I will extend this. Then, from the point B, I said maps to some other region here, call this A. And this is F of U intersect. And then from the point B, we also have a mapping G, as I denoted before, that goes to some other copy of Rn. And I said to call this point C. So this is G of U intersect. So this should be G of B, and this should be G U intersect. Because that's where we're taking the map. And I said there's an inverse mapping F inverse, and similarly for this. Sorry? U, oh no, that's very bad. It's very bad. Thank you. Okay. So, ignoring all this, what am I basically doing? What I'm saying is that our manifold is very general. It contains a bunch of regions. And each region locally maps to some copy of Rn. That's it. That's all I'm saying. So you can make some region, so this is some point, and this is a neighborhood around that point. You can map this neighborhood of this general manifold to some locally Rn. And Rn, I just mean it, right? So this is like R3. This is R2. And so that's all I'm saying. And in this process, I've told you how to define a coordinate transformation. So this machinery starts to allow us to talk about vectors on more general curve spaces. Because you can see now, if I have some general curved space, I can make it locally look like Rn. So I can define my vectors now in some local region of my general space, which looks like Rn anyway. And all my work is happening in here. I actually don't need to worry about what's happening. So that's the idea. But I need to go a little bit more.
So you use the manifolds to allow to represent the entire different.
Yes, yes, yes.
And then you transfer it to the local items to be able to work on.
Exactly, exactly, exactly. And this is the genius of Riemann, actually, who came up with all this. But anyway. Question? Yes.
So, now what you're doing is you create a ordinate transform through a manifold, right? But how do you make sure that you have that exist manifold which satisfies all of that?
That's guaranteed by the fact that I'm considering Hausdorff. That's why I was fussy about Hausdorff. If I do not have that, then I cannot be as nice as I am. So Hausdorff, because I can separate points into neighborhoods, I can map those neighborhoods uniquely into copies of it. So that's why I was fussy about having Hausdorff. But I will make it more clear. Okay. So,
Find those mappings, so sometimes you make the Jacobian to the coordinate transformation. Do you find those to
there's a difference. You can always find a mapping, but you could find a really bad mapping. So there's a difference between using what we say good coordinates and using bad coordinates. So for example, transforming from xy to r theta is an okay coordinate transformation. There's no direct singularities in that. So you need to have a well-defined coordinate transformation. So it could be that it's actually pretty hard to do that in general. But in most cases, you can always find one coordinate transformation that works for the vast majority of cases you're interested in. So I'm going to actually talk about it. So now that you have some idea, but if this is too confusing for you, just keep the picture in your mind that I have some general M, and I can make any local region of the M look like Rn. That's it. That's all you need to take away from this. If you want to be more precise, then you can use this, but the basic idea is that any local region of M can be made locally to look like Rn. And this is where your vectors and all these things you're familiar with. Okay? So just take that away. It takes a while. Like, you cannot possibly learn this in a course. You have to read it again. So related to this is a very important concept of what we call an atlas of charts. An atlas of charts. And what I mean by it, so a chart, by definition, is a map of some open neighborhood of M to R. That's what I mean by chart. And in this figure, you can see that F and G are both charts, because they do precisely that. Yes. Okay, so now you can imagine you can have a bunch of charts for them. Because, like I said, what I want to stop, I can have many mappings that go from any region of M to R. I just drew two here, but there's many of them, infinite, maybe. So, we say that a set of charts is an atlas. If that set of charts covers all of it. if it covers. And this is very important. So, let me finish this definition, then I'll ask you a puzzling question. If you're not puzzled already, let me ask you. Okay. Yeah, so this is related to what you did last year. So consider two intersecting charts. Of M. One has coordinates, call it xa, where a is some label that goes up to the dimension of it. With coordinates xa, and the other one has coordinates ya. Let me define this quantity j as the determinant of the following matrix, namely partial xa with partial y, or other way around. Determinant dya or dx. Do you remember when you were doing volume integrals in your multivariable calculus class? Have you done volume integrals, surface area integrals? If you're in some weird coordinate system, you have to add a Jacobian factor. That's where this comes from. You have to account for the fact that you have some extra fudge factor to make that integral well defined. So it comes from this idea. So J is the Jacobian. So I've defined a Jacobian matrix now. This is a matrix that relates these two chunks. In one in coordinates xa, one coordinates y. And if you're confused, go back to the case when you were trying to integrate something over a circle. You always have to put a Jacobian factor there. Of like r squared equals theta or something.
So
it's exactly the same.
So is it a scaling?
Exactly, exactly. Because you're going from essentially integrating over a square to integrating over a circle. So there's some weird transformation that's gone that you have to take account of. So this is what the... Yes?
So for the Jacobian factors, should we be determined of the delta ya or delta xa, not xb?
I want to keep the indices different in case that you have more coordinates in one case compared to the other. So I don't always have to go from the same dimension, right? I can go from R3 to R2. So I want to make that case too. Oh, and I just want to say, so if J does not change sign at all on M, then we call M oriented. And further, you know this from your calculus course. Good, I think I will have time to ask you the question. Good. Okay. And further, if the j factor here, which is the determinant, does not equal 0, in any neighborhood of 1 point, of any point in M, then there is a one-to-one inverse, as you know, coordinate transformation in that name. So this answers your question, probably. You have to be, when you're choosing coordinate transformations, motivated by this idea that the Jacobian should not be 0 in your transformation. So this helps you define. Okay, so let me ask you this question now. Yes, let me, as I said, a manifold can be anything you want it to be. So let me make it a sphere for you. So consider once again my three-dimensional or two-dimensional sphere. I've always wondered, is it three-dimensional or two-dimensional? Sphere? Yeah. Why should it be three though? Because your z is a function of x, y. So is it 2D or 3D? I don't know. I've always had this fussy about. Anyway, because you only have two. Okay, let me get to my question. So let me denote this sphere as the set of all x, y, z. So you've seen this before, but in R3, such that x squared plus y squared plus z squared is equal to 1. So the unit sphere. You've drawn this to make. So that's my manifold. It's this sphere. And I've written by this equation. My question is to you, how many coordinate systems or charts do I need to cover this sphere exactly? Can you find me a system of coordinates that will cover this entire sphere? And if so, how many such coordinates do I need? So remember, a chart takes an open neighborhood of my sphere to some open neighborhood of Rn. So my claim is that there's 6 of them. You need 6 coordinate charts, 6 set of coordinates to cover this sphere. What are they? In 1 minute.
2, and you have 3, 4, and one in the middle, and I don't know the 6th one.
You're very close.
The side?
So the northern hemisphere, the southern hemisphere, eastern, western, what about the other two? It's the same as east-west, but just rotated 90 degrees. Right?
Oh, yeah.
So you have rotations around x, 2 rotations around y, and 2 rotations around z.
So you just get Ex, Y, directions.
Exactly. Yes. You see that?
Yes.
That's what I mean. So this is a helpful way of visualizing what I mean by charts. If you have, manifold can be anything you want it to be. So in this case, I'm considering it to be a sphere. But I need a set of coordinates. There's not one set of coordinates that you can use that will cover the entire sphere. It just cannot be. So you can have one for here, one for here, and then I guess one for the other direction, which I cannot do it on the board. Any questions about this?
Is there a rule, like, if it's n is equal to 3, then it's 6, or...
Not that I know. Not that I know. Actually, 6 is the systematic way of doing it. There's one way you can do it, that there's precisely 2 charts that will cover the entire sphere. And if you ever open Atlas, you know what the answer is. It's stereographic projection. So that's the way to get to. So it's very related. It's called Atlas of Charts because it's supposed to make you think of the Earth. So how many ways can you... There's no one way to draw a complete flat space picture of the Earth. Right? You need many types of charts to do it. So an atlas has things that project the upper hemisphere or southern hemisphere. That's why it's called an atlas of charts. So many coordinate charts need to cover the surface of the Earth. Exactly. So I will continue now that we've set up this material. Next on Wednesday, I will finally get to value the function. Okay, good.